Let's take a look at another example of finding the derivative at a particular angle value for a polar curve. Here we have the cardioid given by the equation r equals 1 plus sine of theta, and we are asked to find the slope of the tangent line when theta equals pi over 3. Recall the equation for obtaining the first derivative, dy dx, of a polar curve, r cosine theta plus dr d theta times sine of theta, all over negative r sine theta plus dr d theta times cosine theta. Finding dy dx for this particular polar curve, we have our r value, which is 1 plus sine of theta times cosine theta, plus, now we need dr d theta, so if we find dr d theta from the r equation we are given, that simply is cosine theta. So we have cosine theta times sine of theta. So that's our numerator. In the denominator, we'll have negative the quantity 1 plus sine of theta times sine of theta, plus our dr d theta that we just found, cosine theta, and that gets multiplied by cosine theta as well. This is going to be an example of a problem that once we start simplifying, we do have opportunity to use a couple of our double angle identities. Use of those are not necessarily mandatory, but they do make your calculations a little bit simpler. If we simply rewrite and combine some terms here, if we start distributing, we need to first distribute the cosine over that quantity of r, 1 plus sine of theta. When we do that, we have cosine theta, then we have cosine times sine, but notice we have another cosine times sine over behind the plus sign. So when we combine those, we have 2 sine theta cosine theta. Of course, you could put the cosine theta first, according to the commutative property for multiplication. Distributing in the denominator, we have to distribute both the negative and the sine. That gives us negative sine of theta, and then a negative sine squared of theta, and then behind the plus sign, we have cosine squared of theta. This is where we have opportunity to use some of our double angle identities. We'll keep the cosine theta that's in the numerator, but 2 sine cosine of theta is the double angle identity for sine of 2 theta. Again, use of these double angle identities is not necessarily mandatory, does really make your calculations a little bit simpler. In the denominator, we have negative sine of theta, and then notice we have minus sine squared of theta plus cosine squared of theta. Well, that's the identity for cosine of 2 theta, which states that cosine squared of theta minus sine squared of theta. So this becomes plus cosine 2 theta. Again, not necessarily mandatory, but does make your calculations a little bit easier. Now we can go ahead and find the specific derivative at the angle of pi over 3. Once again, using our unit circle knowledge. So we have cosine of pi over 3, which is a half, plus, now we have to multiply that pi over 3 angle by 2, so that gives us 2 pi over 3, and then take the sine of that, which is square root of 3 over 2. In the denominator, we have the opposite of sine of pi over 3, so that's going to be a negative square root of 3 over 2, plus, once again, we have to multiply pi over 3 by 2, giving us 2 pi over 3. Cosine of that is going to be a negative 1/2. So that's what we have so far. Easiest thing to do is to multiply everything through by 2 so as to simplify the complex fraction. Doing that, we have 1 plus square root of 3 over negative root 3 minus 1, which simplifies to negative 1. So therefore we have, at the point on this curve where theta is equal to pi over 3, we have the slope of the tangent line being negative 1. So let's take a look at this on our graphing calculator and confirm that is the case. Under r equals, on our graphing calculator, we're going to have 1 plus sine of theta, which is the equation for the cardioid that was described to us. I'm going to go ahead and do zoom trig And this is what a cardioid looks like. Remember that we can do second trace, and the second option there is dy dx, and we want at the angle of pi over 3. So simply type in pi over 3, hit enter, and you'll notice the slope there does equal -1. And if you imagine a tangent line drawn there to the curve where theta equaled pi over 3, it definitely has a negative slope to it. So it makes sense that the slope could indeed be -1.